Okay, now we can do something more interesting than just straight lines and planes. A path is a function from a time interval into 3D space. So here I've plotted a few paths. They look pretty neat. I've written the x, y, and z coordinates vertically just to save space. Then a curve is the image of such a path, so all the outputs of that function. The reason for distinguishing between a path and a curve is, for example, two different paths could traverse the same curve, but at different speeds. We can also express a path as a vector function by considering the vector from the origin to that point, and then we can express the components in terms of the standard unit vectors I, j, and k. We call these individual functions, f, g, and h, the component functions of this vector function. So thinking of it as like one function with a vector output is more efficient than thinking of three functions with scalar outputs. It's sort of all packaged into one object, but functions with scalar outputs are more familiar. We already know how to work with these. For example, we're going to be interested in the tangent vectors of paths, which is given by their derivatives. So how do we take the derivative of a vector function? So I'll go through that more slowly and carefully in the next video. But for now, all you need to know to calculate them is you just take the derivatives of each of the individual component functions. That we know how to do. So the tangent vector represents velocity. If you think of r of t as describing the position of a particle in space at time t, then r prime of t will be its velocity vector at time t. Then the tangent line of a curve at a point is the line which goes through that point and which is parallel to a velocity vector you could have at that point. So it's the line of all possible velocities you could have at that point on the curve, traveling on the curve. To understand the difference between a tangent vector and a tangent line, let me emphasize the tangent vector depends on the path and the time t. So if two paths trace out the same curve, but one is going at twice the speed, then their tangent vectors at a point will be different. Same direction, but different magnitudes. Whereas the tangent line only depends on the curve. So, for instance, the green curve has this crossing point at t equals 0 and pi and negative pi. So the tangent vector there depends on which way you're approaching it from, so the value of t. And since there's two possible directions here, we'll say that the tangent line to the green curve is undefined at this crossing point. So we'll want to try to avoid curves like this. Okay, so here's an example. We're given a particle moving in the xy plane according to -2 sine 3ti plus cosine 3tj. And so part A asks us to find an equation defining this curve, like an implicit equation for this curve. So for this, we'll use that cos squared plus sine squared is always 1. So here we have sine 3t is -x/2, and cosine 3t is y. So the equation x/2 squared plus y squared equals 1 will define the curve, which is parameterized by this path. Then for part B, we want to find the velocity and acceleration vectors at time t equals 0. So to differentiate a vector function, we just take the derivatives of the component function. So that'll be -6 cos 3t times I minus 3 sine 3tj. And our double prime of t will be 18 sine 3t times I minus 9 cosine 3t times j. Now we evaluate these at t equals 0. So sine of 0 is 0. This will be -6i. And our double prime at 0, this will give -9j. Next, we're given a particle moving on the unit sphere, and we're asked to find its velocity and acceleration vectors at t equals pi. So if that's our function, then its derivative is going to be, let's see, so sine 2t, so this will be sine 2t cos 2t times I minus 2 cos t sine t times j plus 2 cos t sine t k. And there's various ways you could rewrite this using the double angle identities, but we don't need to. Okay, so that is the velocity at a general time. Then the acceleration at a general time will be, so will give us cos squared 2t minus sine squared 2t times I plus 2 times sine squared t minus cos squared t times j plus 2 cos squared t minus sine squared t k. All right, now we just need to evaluate that at t equals pi. So r prime of pi is, well, since they all have a sign in them, and sine of pi is 0, and sine of 2 pi is 0, we get 0. So it's the 0 vector. For the acceleration, r double prime of pi, that's going to be now, so cos, so we get I, and then negative cos squared, so cos of pi is -1, but then we square that, so minus 2j, and then plus 2k is the acceleration vector. Finally, let's say we're given a particle traveling according to ti minus t squared j plus t cubed k, and we're asked to find its speed and direction when t equals 1. So first we find the velocity of the particle, so that's just the derivative of this function. That'll be I minus 2tj plus 3t squared k. Then we're interested specifically at the point r prime of 1, so that'll be I minus 2j plus 3k. So the speed is the magnitude of the velocity. So the speed will be root 14, and the direction means the unit vector of the tangent vector. So we divide the velocity by the speed. The direction will be the unit vector 1 over root 14, I minus 2j plus 3k.